All right. So there is homework due this Wednesday, and there's also homework due next Wednesday. Keep that in mind. We kind of ran up against the wall here, and I was trying not to make too much due this week. And so the homework that's due next week, I probably won't put on the final exam. I know it's a topic on the final exam sheet, but seeing how the homework will be due after the final, technically, I probably won't put it. I won't put it on there. I'll just tell you that. And instead, you'll just be quote unquote tested on it by answering homework. I'm also going to drop the lowest 10% of homework assignments. So keep that in mind. If you got a really good, perfect homework grade or close to it, you could just not do a couple homework assignments, and your average would stay the same. Okay, so we've got 2 homeworks due this week. Our final exam is going to be a week from tomorrow, so a week from Tuesday. During our normal final exam period time, that's the time I was told to use. I've mentioned this a lot now, and so I hope you can tell me ASAP if that problem or if that time is a problem for you. I'll also mention that on the final, you're welcome to bring in some notes. So you're welcome to create an 8.5 by 11 sheet of paper, just like a normal standard size piece of paper with your notes on it. And so over the next week, as you're studying, you might want to be building that note sheet up. All right. Questions about the end of the semester, final exam, stuff like that before we get into any material? Okay. So the homework that's due Wednesday is on 4.5 and 4.6, and I have a couple homework questions from those. But let me just review what's in there really quickly. So first of all, 4.5 talks about the dimension of a vector space, right? And so it's talking about, it says if we have a basis for a vector space, however many, let's see here. That's not what I want to say. I want to say this. However many vectors are in, that's not what I want to say either. This is what I want to say. The dimension of a vector space is however many vectors are in the basis. And to remind you what a basis is a set, this is from 4.3, it's a set of vectors that are linearly independent and span the space. And so when you think about the dimension of a vector space, it actually means the kind of thing that you think it means when you hear dimension. Like if I said this is 2-dimensional or 3-dimensional, that's referring to both the number of vectors in the basis, but also the physical dimension of the space, right? So just for example, if we had these 2 vectors, 1, 0, and 0, 1, those are in R2, and we know that that's called the standard basis, right? 1, 0 is this vector right here. 0, 1 would be this one, or vice versa, actually. Right, that's like E1, E2, E1, E2. And then we know if we do the span of those 2 things, it creates the whole plane. And if I gave you a piece of paper that looked like that and I said, what dimension is that? You'd probably say it's 2-dimensional. And it's 2-dimensional in the physical sense, like there's 2 dimensions here, right? It's a flat piece of paper. But it's 2 dimensions in the sense that there are 2 elements in the basis. Now, if we took a third vector and we stuck it out the page, so my pen becomes the third vector, right? It creates the z-axis coming out the page. That creates R3. And so there'd be 3 elements in that set. And we know that R3 is 3-dimensional, right? Like our world that we live in is 3-dimensional. So just trying to relate the fact that the word dimension means what you think it means physically in terms of like an interpretation. And then mathematically speaking, it's how many vectors are in the basis. So I did have a question from that specific homework set, but is there any, and here's kind of the pictorial representation of what I was saying a second ago. This is on page 19 of the notes. This is showing a straight line through 3D. And so that straight line is 1-dimensional. It's 1-dimensional in the sense that it's a line. And it's also 1-dimensional in the sense that it's the span of a single vector, right? But as soon as you add a second vector, which would be this piece of paper right here, it becomes 2-dimensional. And when we add a third vector, it becomes three-dimensional. Okay. Yeah, I see Adrian asking a question about the final. It's 2:30 to 4:30 on the 12th. And it says that on every single announcement sheet that I've posted on Blackboard for the last month or so. So please don't tell me it's not on Blackboard. It's on Blackboard in lots of places. Every single one of these announcement sheet, which I post every single class period, has had the final exam on it for about a month. Okay, sorry, I just rambled a little bit about the notes. I was trying to just clarify a few things. And then sort of the last part of that then is we know that when you look at the pivots in a matrix, so you get a matrix, you row reduce it, you look at the pivots, we had learned previously that the pivot columns form a basis for the column space. And so however many pivot columns there are, that's the dimension of the column space, right? And then we talked about previously how the null space is the number of free variables, right? That's how you figure out the null space, because you're going to solve for free variables in that case. And so that means however many free variables are, that would tell you the dimension of the null space. Okay, so I had this particular question that I'm happy to go over, but are there questions about the notes based on what I just said at all before we look at this question from this section? Just looking for general questions from 4.5 before I look at this particular homework question. I'm just going to pause a second in case someone's typing. Okay, so in this particular question, we're given a matrix, here it is, A, and we're given the reduced form. So we're just being told that when you do RREF, it becomes that matrix. And so we can see there's a pivot right there and a pivot right there, and then we have a free variable, right? So x3 is free, x1 and x2 are pivots. Okay, so let's answer this question. So we're given A1, A2, and 3, we're being told are the columns of A. So this is like A1, this is A2, this is A3, columns of A. And beta is the collection of the three columns, right? A1, A2, A3. And H is the span of those three columns, right? So the span would be C1A1 plus C2A2 plus C3A3 for any C1, C2, C3. So the first question is, how many vectors are there in beta? Well, beta has 1, 2, 3 vectors, right? There's 3 columns, and so there's 3 vectors in beta. But H is, so the second question is how many vectors are in H? H is any linear combination of the vectors and of the columns, I mean. And so you can pick anything for C1, C2, and 3, and so there's infinitely many possibilities there. And so how many vectors are there in H? Infinity. All right, so this question is just trying to get at, hey, when we just list vectors, you're counting them, but when you say they're a span, all of a sudden there's infinitely many of them. Is that okay? I'll stop there, see if that's okay. And so the next question is, what's the dimension of the subspace H? Well, H is the span of the columns. And so another way we can think about H is the column space, which we denote like this, col A, right? And so what we just said in the notes was the number of pivot columns tells you the dimension of the column space. And so in this particular one, there are 2 pivots. And so the dimension of the column space in this one is 2 because there's 2 pivots. Right? In other words, there's 2 vectors in the basis for the column space. Is beta a basis for R3? Well, in order for it to be a basis, let me write this down here. D. For a basis, I just said this a second ago, but what we need is A, linear independence, and B, we need them to span the space. And since this is a square matrix, in both cases, that would mean that there's no free variables, right? If we have linear independence, that means that the solution to the homogeneous equation is the trivial solution. And if we wanted to span the space, we need to pivot in each row. And so both of these things, since we have a 3 by 3 matrix, means that there would be no free variables. But we have a free variable, right? So there's not a pivot in the third row, so it doesn't span the space because we're missing a pivot in the third row. And they're also not linearly independent because we have a non-trivial solution, right? We'll have a free variable. So both those things fail here. And so both fail. And so is it a basis? No. The last question is, what is a basis for H? And again, that goes back to the thing I put up here a second ago. If we want a basis, oh, actually, that's from I think 4.3. But let me see if I can find that page real quick. When you want a basis for the column space, which is what that one's asking us for, got 4.3 right here. In 4.3, so page 3 on chapter 4, excuse me, page 13 on chapter 4. What we said was the pivot columns form a basis for the column space. And so if we want a basis for the column space in this case, then we want to use the first and the second column because those are where the pivots are. And so we don't use those columns. We go to the original one and use those two. And so I'm not going to write that out, but we'd use the first two columns of A because they're the pivots. And so this question actually isn't asked, but another question that could be asked is, what's the dimension of H? Right, that's not asked here, but maybe I'll just write that down at the bottom. Any thoughts about that? What's the dimension of H? I'm throwing that out there. Right, so H is the column space, and we're saying the first two columns form a basis for H. So what's the dimension of H? 2, right? Yeah, so there's 2 elements in there because it's the first 2 columns. So the dimension would be 2 because there's 2 columns in the basis. Okay. Other questions about this particular question or other ones in 4 or 5? You know, I don't want to scare people away. I know last time I was sort of saying, please send me stuff ahead of time a little frustratedly. I don't want to scare people away from asking questions during class. You're certainly welcome to look through the homework and ask some questions. It just helps me help you if I have a chance to look at the question just for a minute and, you know, think about the right way to present the answer and things like that. So that's why I was able to sort of explain this one without any bumps or anything, just because I had a second to think about it. But anyway, I don't want to deter you from asking questions. So if there are other questions that you didn't send me ahead of time, I'm happy to still look at them. Anything else from 4 or 5? I have a couple from 4 or 6. Anything from 4 or 5 before we look at 4 or 6? Okay. So in 4-6, here's the main thing about 4-6. So 4-6 is all about rank, you can see here. So let me just say one thing about rank. So the word rank just means the dimension of the column space, right? And so we know that we just said a second ago that the dimension of the column space is just the number of pivot columns. And so with that in mind, this becomes a pretty important relationship. The rank plus the dimension of the null space equals n, right? So n is the number of columns, and we know rank is the number of pivots, right? Well, it turns out that null space, as a reminder, the dimension of the null space would be the number of free variables. So all this is saying is when you add the number of pivots plus the number of free variables, you're going to get the total number of columns. And so everything in 4.6 is mostly based off this relationship and trying to reason around sort of like what you're given and then what you can figure out using this relationship. I feel like I'm missing a page here. Page 20. So page 21, this is not a one-page section, right? I don't know what happened to the rest of this section. going to show a couple of the examples here, but it seems as though I've misplaced my other page, or pages. Anyway, let's jump right into the homework questions. So the first one I had was this one, 4.6 number 2. And it's telling us that A is 13 by 8. And so, you know, the n then in that equation, let me write down the equation. So the equation was rank plus the dimension of the null space equals n, the total columns. And so we're being told it has 8 columns, right? So we're being told that n is 8. And it says the dimension of the column space is 6. And so the dimension of the column space being 6 means that rank is 6. And so, yeah, right. And so that means that that's interesting. Yeah, so if rank 6, that means there's 6 pivots. 6 pivot columns. Well, each pivot has to be in its own row too, right? Because in order to be a pivot, you need to go down and right. And so that implies that there's 6 pivot rows as well. If you just imagine what a pivot is, it means there's a 1, and then you go down and left, and when you go down, you go into a new row. I mean, down and right. And so if there's 6 pivot columns, that means there's 6 pivot rows. And so the question here is, what's the dimension of the row space? Well, the number of pivot columns will tell us the number of pivot rows, and so it turns out the dimension of the column space and the row space are the same. And this is not something that I think was in the, so this implies that the dimension of the row space and column space are the same. This is not in the notes, but I thought it was something that was fair to sort of reason through. And so if the rank is 6, that means the dimension of the row space would also be 6. Yeah, so the dimension of the row space in general should equal the dimension of the column space. That's correct. Okay. I'll pause there and see if there's other questions about that one. That one seems okay. Okay, the other question I had was this one from that section, 4.6 number 5. And so we're being told A is an n by m, so we're not being told those dimensions, but we're being told the rank is 3, and we're being told the nullity, so maybe that's a word, I can't remember if I put that in the notes or not. Nullity is the same thing as the dimension of the null space. And we're being told that that is 4. Yeah, that looks good so far. And then the third thing that it says here is that the column space is a subspace of R9. So what does that mean? What's that telling us about? Like, these things seem to apply to the equation, right? Rank plus nullity equals total number of columns. But what is this part telling us? Column space is a subset of R9. Someone type something? I may have missed it. 9 dimensions, yeah, that's right. So this is telling us that the columns are 9 by 1. Right? In other words, there's 9 rows. Right? Because each column is a collection of rows. And so so the question here, maybe I should have started there. The final question is, what's the dimension of A? And so, in other words, it has 9 rows, so that's n. And then we use the equation to get the other piece. So we know that rank plus nullity equals number of columns. and we're being told that those two things are 4 and 3. So 3 plus 4 equals number of columns. And so 7 is number of columns. So this thing is a 9 by 7. Oops, that should be 7. Sorry. Questions about that one? Or others in that section? Who's in 5-4? I mean 5-6? 4-6, my goodness. I'll just turn it open to any questions. Any questions at all. You know, the homework or the section for today was eigenvalues and eigenvectors, which is a very important kind of culminating section that appears in lots of other classes. Like if you take another class with me, an upper level class, you'll probably see eigenvalues and eigenvectors again. So that's what you should have watched for today, but I know that the homework for this week is on other stuff, so maybe people are focusing on that. But I'm happy to talk about that video as well, if people would like to. Anything at all? Oops, I just saw the type question, sorry. Number 1 on 5-1. Sure, let me pull that one up.
Yeah, that one's kind of difficult. I was able to do it, but there's like one really weird question on it because it's like one of those like check off which ones are true and which ones are false. And there's one that's like deliberately trying to trick you.
Yes, okay. Mm-hmm. So let's see here. Give me a second to write it. So this is 5.1, number 1. And it says we have a square matrix. And then we're being told to mark these true. Check the true statements. Let me give me a second to get this on the screen. So the first one says A not invertible if and only if 0 is an eigenvalue. So that's true. That's part of the invertible matrix theorem. So in this section, this is the last section we tack onto the invertible matrix theorem. That's just one of the things that's part of the invertible matrix theorem. Because here's what we do, by the way. So AX equals lambda X is the relationship we're looking at. We call lambda the eigenvalue. And we call X the eigenvector. And so if 0 is an eigenvalue, then lambda is 0. And so the right-hand side of this would be 0, and we would have AX equals 0. Excuse me. And that would have a non-trivial solution, which implies that it's not invertible. So that's why it's part of the IMT. B says a number C is an eigenvalue. So lambda, one of the lambdas. Lambda is a real number, by the way, and X is a vector, for those of you who haven't watched this video yet. So a number C is an eigenvalue if and only if A minus Ci X equals 0. That's also true. That's the definition of how we find eigenvalues. So if you haven't watched these videos or looked at these notes, you're probably just like, how do you know that? That's just like what you're being told in the notes, essentially. And I show you how you get that, but that's the definition of finding an eigenvalue. So that's true as well. C says if AX equals lambda x, then lambda is an eigenvalue of A. This is the one that they're trying to trick you with. Yeah, this is the tricky part because it's not specifying that x isn't 0, I think is the tricky thing there.
Yeah, that's it.
So this is why you're right. This is kind of a, I wish they didn't do this kind of tricky stuff, but this is a false one. So we need, in order for something in x to be an eigenvector, x shouldn't be the 0 vector. And so this would be true if x equals 0 for any lambda, right? So if it's specified that x shouldn't be 0, then it would be a true statement. But since it's not specifying that, I believe that's why it's false. So I apologize that that one was a little bit tricky, but you're all here listening to that, and I hope you'll remember to go back and look at this one when we do it. The rest, I think, are sort of straightforward. So D says finding eigenvector of A is hard, but checking if you have one is easy. That's also kind of a dumb one, but that's true. So finding one means solving AX equals 0. Excuse me, A minus lambda x equals 0. That requires some row reduction, but just checking to see if you have one just is multiplying two things together, and so that's easier. But again, that's kind of like a opinion, probably, so that's also kind of silly. But hey, we're going over this one together, so you should get this one right. And then the last one is false. It says finding eigenvalues of A means row reducing A. That's not how you find eigenvalues. And if you watch the section, you'll see how to find them. It's doing this. Oh, that's eigenvectors. Oh, no, that is eigenvalues, yeah. So we just said that B is how you find them, not just row reducing A. So the true ones are A, B, D. In this particular case, it's possible yours get rearranged in a different order depending on how yours is generated, but this is how this one was generated. Happy to clarify any of those questions if anyone has one. Any questions about that one or any of the other ones? Any other problems? Excuse me. Okay, you guys are working hard. I appreciate that. Let's finish strong here. You know, there's only a week left, I know. I'm starting to fade too. It's very weird just being at home and just trying to motivate yourself to do all this stuff. One more week. We can all do this. Prepare with the final, with a note sheet, you know, trying to reduce the amount of stress there. Just finish strong. One more week. And we got this. Let me know if you have any questions. I'm going to post this video, and you're welcome to check it out later. And I'm also going to post the notes as well.